All right, welcome everybody to today's webinar. Our webinar today is on water level sensors and technologies, as well as best practices with installations and reviewing sites and installations. Everyone at this point is on mute. This is being recorded so that we can rebroadcast it. And if you're not on mute, it makes it, there definitely becomes background noise for the rest of the folks. By way of some housekeeping items before we get started, we plan to answer any questions that you may have. If you will put those in the chat area, we are going to respond to questions at the end of the webinar, and we hope to get to as many as we possibly can. Again, if you'll stay muted, that would be great as well. Today's webinar will be presented by, I call them a couple of experts that I think they're uncomfortable with that, but Brad Schaefermeyer, one of our presenters, covers our Western hydrology sales. Brad's been in the industry for 33 years. I've known Brad for many years. I've known him to cover both domestic clients as well as international. Brad's traveled the world. He's installed gauges throughout the world. He is quite well-rounded, understands the industry well. He's actually quite technical. Brad has a bachelor's degree in electrical engineering. So we're excited to hear from Brad today. Along with Brad is Jim Wellman, who covers our central hydrology sales. Jim's been with AE Monitoring for 6 years. Prior to that, Jim worked for 29 years with the U.S. Geological Survey, where he installed hundreds of gauges, was a field office chief in Tulsa, Oklahoma for many years, managed that office and those cooperators there as well. Developed and designed and enhanced many hydrological networks, as well as advanced monitoring techniques. Highly experienced in analyzing and making decisions that improve hydrology methods to collect and monitor and publish hydrologic data. Jim is quite sharp in this industry. He is our go-to when we have questions about installs and products and different technologies and so forth. My name is Gary Baker. I'm going to be moderating this webinar. I manage the hydro sales for FTS, One Rain, and High Sierra Electronics. So we'll get started and talk about water level measurement methods. Getting started with this, and when considering what types of sensors and equipment to put out at a site, it's important that we understand our site characteristics. Every site is unique, and it's important that we take an evaluation and understand the characteristics, the physical characteristics, while selecting sensors. It's probably a good practice to utilize existing structures. If we can use structures that are already out there, that can certainly save us time and money. Sensor locations. It's good to look for the best proper location for the sensor. That will enhance our accuracy and reliability, as well as low maintenance cost. Over the years, I've had many people ask, hey, what's the best sensor to use for collecting surface water data? And I'm of the opinion there's not the best sensor, there's the best sensor per site. And so again, it's important to understand the site and characteristics. There may be sites where you want to consider multiple sensors at critical locations where a sensor may get damaged. Then you can go to your backup sensor and so forth if it's critical. information. Site considerations, again, do you have a structure in place that you could use? Can you mount an orifice line or mount a radar to that site? Do you have rapid stage changes? Is it a flood site? And if it is, do you get high velocities of water going down? Do you have debris in the water that can affect your data as well as your equipment? Is the site dry a good portion of the year? Is it a secure site? You have to worry about vandalism. What's your budget? Do you have a controlled pool that you could utilize? And again, is there possibility for multiple sensors? Is that a requirement at the particular site? And that could be a consideration. Before I turn this over to Brad to talk about the different methodologies, I think it's important to know that AEM is working on a number of different methods for measuring water level. However, today we're going to talk about the most widely used sensors today and why and when would you use those. So with that in mind, we're going to turn it over to Brad.
Hey, thanks, Gary. Appreciate being here today and excited about the opportunity to present. Looking at this slide, you know, there's a lot of technology that's evolved over the years and for measuring water level. And in the simplest terms, I guess, is many of you may be familiar with looking along the river or involved yourself, but staff gauges are common to be able to view the current reading and have a visual. We talk about some future, as Gary mentioned. We'll briefly talk about some of those things, but staff gauges are extremely useful in that part of making measurements, at least to visually, and those have been around for many, many years. The other one, the next to it, is the strip chart recorder slash shaft encoder. We'll talk about that. The method of doing this has been around for a number of years. We'll highlight that as well. Then there's the pressure transducer that is common in the industry and in measuring water level in rivers and so forth. And it's been extremely reliable and robust over the many years. Some of the newer things that have come out actually kind of got these switched a little bit, but the radar sensor in the bottom left is come out in the last probably 15 years, and within that it's a non-contact method of measuring water level in rivers. And incidentally, in all of these, as Gary mentioned, you know, there's no method that fits all. And all of them are unique, and Jim was going to get into details on that. But radars being a non-contact method of doing measuring water level is extremely reliable, and it has its place. Bubblers, in addition, they have evolved over many, many years from some of the early stages of nitrogen tanks. We'll talk about those into the self-contained bubblers. And the last one, at least, we'll go into detail on is the acoustic sensors, which are out there that are measuring actual discharge measurements flow, and so they can provide the discharge measurement once the flow is known. Okay. As mentioned, the reference gauges, we'll talk about these briefly. You know, typically a staff gauge had provided and still providing many sites that aren't monitored automatically, but they are also used to provide the reference once a gauge is installed, whether it be a bubbler or radar, to be able to visually see the current measurement, and then that can be adjusted if need be on the automatic gauge. The same thing is true with the reference. This is a style that would be able to provide that reference to be able to make a measurement wire weight there on the right. And so those are the references that allow us to be able to make the reference that is at the site current reading, and then those can be used to set the current stages within the device, whether it be a radar, a pressure transducer, so forth. Okay. Talk a little bit about the shaft encoders, and incidentally, some of the early shaft encoders included the wheel that had the pin and be able to record that, and it was on a drum. It's not shown, it was shown in the previous one, but they have been around since the 1900s. And they have been just extremely robust, and there's many out there that are still in use today. This provides, more recently, beyond the 60s, was digital encoders, which is in the middle photo there, and they provided the means, and they still do today, provide the means to be able to be used using a wheel. It involves a wheel with a counterweight and a tape, either a beaded tape a tape or a beaded cable with a float. And they're typically installed in a gauge house, and there's thousands and thousands of gauge houses in operations in the 1900s, and they were built to be able to house these encoders, these tapes, systems there. And the advantage of putting them inside of the gauge house was, if you look at the bottom, the right picture on the right, it had the intake pipes that would actually stabilize, and actually stabilizes the reading within that gauge house, and allows for the float to rest a little, so it's not as violent inside that gauge house that the river may provide on the water surface. And so they've been extremely reliable. They're still being used today. We won't go into a whole lot of details in encoders, other than mentioning that they are out there, that we still can provide those as well. And again, these devices provide either a sensor only, or they can be a logging device as well. There are encoders out there that log the data as well, but typically they are installed as a sensor and then connected to a data collection platform, as shown in that photo. And then they typically provide either a display readout or no readout at all. And that's kind of a summary of encoder, how they operate, and their use. Next is the pressure transducer. And the pressure transducer, there's a couple of different types, and we'll talk about those briefly, but the theory behind pressure transducer is that they are, of course, mounted in the lowest portion of the water, and they do need to be secured at the bottom or the lowest point up above the silt that builds up, typically in those types of applications. Jim will explain some of those details. But the principle of operation is there's a strain gauge within the body of the sensor that provides the proportional pressure within the gauge, and that will translate to the output in the engineering units, in electronic output that will allow us to measure that in engineering units that we desire. There are two types of gauges, PTs, that are out there, and those are either vented or non-vented. A vented sensor has built inside the casing, the wire casing, a vent tube, which is vented to atmosphere. And obviously, if you're measuring some pressure inside the water, in the body of water, you do need to vent that externally to be able to compensate for any changes within pressure in the air. The other style is a non-vented, which there is no vented vented tube within that casing. And in those cases, you do require a topside barometric pressure measurement, which will allow it to compensate and calculate the difference in pressure. And that in turn, of course, provides the output in the engineering units as mentioned. And so that in the simplest terms is a pressure transducer. And there's thousands and thousands of those out there, and those are still very common use today, and they have their place within the measurement of water level. And now I'll turn the time over to Jim.
Hey, thanks, Brad. And thanks everybody for joining the webinar today and taking time out of your day. As Brad mentioned, Brad's going to, talk about the technology of each sensor. And what I'm going to do is talk about the best practices and some of the differences. And we're actually look at some data as well as some of the different sensors. And really our goal here is to just give you a better understanding of what sensor would best fit your application. So the first one is our pressure transducers, or PT. It's ideal for small watersheds, accurate during normal and rapid stream stage, simple setup, connection to external logger. It's quite simple. You just hook 2 or 3 wires to your logger, and then water temperature output in addition to your water level. And that doesn't come with every manufacturer PT, but it is an option, and it could be useful to better manage your PT. For example, you can utilize the temperature portion of your PT to see perhaps if your PT is out of the water. You can monitor the ambient air and give an idea that, hey, my PT is out of the water. Also, the PT provides a lower cost sensor. It allows for shallow water deployments. You can see in the upper left image, it's a small stream with very, very shallow depths. And the sensor is just deployed in that stream. They're very easy to install. They're very flexible. They can install in most streams. Also, it's important to secure communication line and PT, obviously to protect the communication cable, but also protect the sensor as well. You can house it in a protective conduit. One really good best practice is to install perpendicular to the flow, and also as indicated in the lower image, multiple PTs for redundancy. And we'll talk more about that later. So one of the best practices is to, for your PT with the atmospheric vent tube, is to replace desiccant regularly. If you fail to do so, moisture can get into the vent tube and cause some erratic readings or possibly drift. Another good practice is to monitor the drift, and that you would do that by each inspection. You would look at your staff gauge, and if you start seeing drifts from each inspection, it's kind of giving you a message that, hey, this sensor is drifting, and it may be moisture in the vent tube. And also monitor erratic readings. So all of a sudden your PT is going along well, and all of a sudden you see some erratic readings, and it's really the PT saying, hey, I probably have some issues, whether there's some moisture in the sensor or possibly it's buried. But it's a good indicator to look at those erratic readings, and it's generally giving you an indication that something's wrong with your PT. It's always a good practice to clean debris away from the sensor. And then if you're at the site, just inspect it regularly to make sure your PT is secure. If it's not secure, it's going to have movement, and it's going to cause some inaccurate readings. Also, you want to check your manufacturer recommended calibration. Each vendor is different. Some vendors suggest to send them back for calibration. Other users will simply take the sensor back to their warehouse or test facility and put it in their test tube to determine that it's reading accurately.
Hey, thanks, Jim. Good information about the PTs. Really valuable. We're going to switch over now and talk about the bubbler. The bubbler kind of has an interesting history in where we're at today with self-contained bubblers. But back in the day, years ago, the bubbler, and still today, because they are still being used in the method that's shown on the left, the bubble gauge, the technology and how the measurement is made was designed to sense the water within the column of water through a vent tube installed at the lowest point in the water. And in this case, the nitrogen tank provided the pressure, and then of course a pressure regulator to be able to regulate that flow of air, and that flow, of course, will go through out the orifice into the water, and then it would require a pressure sensor to make that was an external pressure sensor, similar to what basically a PT, that would make the pressure measurement that how much pressure it was required to force a bubble out the end of the orifice. And of course, it was, once that pressure is made, then it was converted, of course, to the engineering units that's desired. And so that, in the simplest terms, that is how the early bubblers were operated. And again, there's still many that are still out there operating just in this exact manner. However, over the years, technology has changed, and many manufacturers out there have developed a self-contained bubbler system that allows all of those things on the left to be housed in one box that includes a tank, a pump through a manifold, and provides automatic bubble rate flow and control through that box. And again, it directly correlates to the level of the body of water that it's placed in. And within the bubbler is the ability to make bubble rate adjustments, setting stage. Currently, many manufacturers out there have displays to be able to set that stage based on those staff reading gauges previously mentioned. And they provide the extremely reliable method of measuring water level. And Jim's going to get into some more detail on that as far as those applications. Incidentally, the other important thing with self-contained bubbler systems is the need to have dry air flowing through that system, and that provides basically a laboratory with no electronics in the water, a laboratory measurement, if you will. Okay.
Hey, thanks, Brad. So on the image here is a typical bubbler gauge that's installed not on a structure, but in near the river on a bank. As you can see, the gauge hut in the darker gray image, that's going to be your bubble system. And actually, how it operates is the orifice line is downward into the buried in the ground, and it's in a downward fashion. And then at the end of the orifice, as you can see, the bubbles in the water, that's going to be the end of your orifice. Bubblers provide accurate data for a wide range in stream stages. There's a lot of bubblers out there throughout North America. It allows flexible insulation for various applications, whether in this case would be a stream, reservoir, estuary. There's just a lot of applications for the bubbler. One of the advantages is lower maintenance cost. Sensor is safe and secure inside the gauge. As Brad mentioned, you don't have your sensor electronics in the water. The bubbler is safe and secure inside the gauge hut. If an orifice line is damaged during a hydrologic event, there's no need to replace the sensor. You would just rework the end of the orifice line. Orifice line repairs are less expensive than sensor replacement and easy to repair. As far as the orifice line, is the image on the upper left. The orifice line specs are black poly 3/8 outer diameter and 1/8 inch inner diameter. And that's the 1/8 is where the airflow is going to be in your system. The example in the upper right-hand corner is actually the orifice line connecting to a bubbler. And we seal the airflow here with a compression fitting. Orifice line run should be downward as possible to minimize any depressions in line and where moisture may collect. As you can see in the lower image, we have a depression there. You want to try to avoid those kind of situations. You can't always have a straight downward, but it's just a good practice to have. And the reason why is moisture will collect in those depressions and could cause some accuracy issues. It's also a really good practice to enclose the orifice line in protective conduit to prevent damage from animals, vandals, and flood events. This orifice line should be run downwards as possible, as I mentioned. And also when you're in the stream, the end of the orifice should be pointed downward, perpendicular to the flow. Also, it's a really good practice is to place the orifice as close as possible to the reference gauge and in calm water. As you can see in the image, that's a great example where the orifice line is several feet from the incline staff gauge and in calm water. You always want to try to avoid placing orifice in turbulent waters which may cause drawdown. That could be large boulders or some infrastructure. As I mentioned, one of the important aspects of the bubblers, avoid placing line upstream or downstream as flow will cause inaccurate readings. So as I mentioned before, you want to place the end of the orifice line perpendicular to the flow. And the reason why, if you install your line and it's facing upstream, you're going to have increased stage readings. And the exact opposite, if you have your orifice facing downstream, you can have a siphoning effect. And always, it's very important to properly secure the orifice line. As with the PT, if it's moving around, you're going to have inaccurate readings. If it moves, it's not going to give you a really good solid data. And just want to mention the orifice line on bridges. One of the advantages of the bubbler, you can install multiple lines in your conduit. In this application, there's actually 2 orifice lines, and they're utilized for a primary orifice. And if you do have issues with the orifice line, whether it gets damaged or plugged, you can just easily go to the site and switch over to the secondary line. It just gives you a backup sensor, so to speak. One thing to be aware of with high velocities and or debris lodged upstream of piers, variable drawdown may occur. We're going to talk about that later. As you can see in this image, we have an orifice line installed in this pier. There's slight drawdown there. And as I mentioned, we're going to talk about drawdown and effects later in the presentation. Just some of the benefits of the bubbler. It really does provide accurate data over range and stage, whether it's really low or extreme high flows. It's a versatile sensor for a variety of hydro applications. As I mentioned before, the actual sensor is safe and secure in the gauge house. It also allows for lower maintenance and sensor replacement costs. Ideal sensor for base flow, flood events, or long-term deployment. And I have a couple graphs here. The graph on the left is just some minor rises And you can see where the bubbler's tracking nicely with a good trace. And then the image on the right is, about a 30-foot rise. And as the graph indicates, this does a nice job with collecting the data, and it gives a nice trace of the river flow. And really some of the best practices for when you do choose a bubbler, and each time when you're at the site, it's a good idea to purge the orifice line to make sure there's no debris in the orifice line. And if you do have a stream that has heavy debris, you also have the ability to have auto purge at specific times. So simply how this is executed is at a certain time, whether it's once a day or once a week or once a month, your bubbler can be activated to have automatic purges to make sure that line is clear. Another important best practice to remember is to ensure desiccant is regularly replaced. As Brad mentioned, we want dry air going through the system, and if moisture is in that system, can cause some issues. So it's a good practice to look at your desiccator, make sure you have fresh desiccant there, and replace regularly. Also, inspect the orifice line periodically. If orifice is buried in sediment for extended period, one of the things you could do is just purge multiple times. Sometimes when the orifice line is buried, there may be some sand particles or sediment inside the orifice line, and multiple purges generally will get rid of that debris. But sometimes you may have to purge and run a small wire to dislodge any sediment. It's just a good practice if your orifice is plugged.
Hey, thanks, Jim. Good information about the bubbler. Bubblers are extremely effective and have their place, obviously. We'll shift over to the radar right now and talk a little bit about the technology of radars. And obviously, it's shown by this picture. Hopefully, it's self-intuitive here. But the radar is designed to be positioned above the body of water, and it uses sound transmitted to the target and echoed back, and that provides a measurement. The radar is a sensor, and in that it connects to a data recorder, and it has a couple of different outputs optional. Typically in the industry, you use SDI 12, and then also 4 to 20 is optional as well. But it is designed to measure, it's a non-contact designed to measure the surface of the water. And radars require that there's a good reflective surface. At least that provides the best measurement. It will hit any target that you have down there. It'll hit the bottom of the bed of the river if there's no water, but it's designed obviously to measure that distance to that target, which in turn it is translated to stage, and that is the useful part of it, to be able to calculate discharge based on rating tables that are provided previously. And so it's very important that the radar be secure at the top of the structure. In bridge applications, some bridges may have some flexibility as the traffic moves across, but it's important that is stable. Also, the radar operates on a 26 gigahertz band, at least this one here shown, and provides a very high frequency to be able to communicate to the transmission pulse and the echo. And again, another application where radar is used perhaps versus a bubbler, but Jim, I believe, will talk about a little more detail about how you can have multiple or backup measurement, either a bubbler or radar. Okay.
Hey, thanks, Brad, for the technical explanation of a radar. So, one of the advantages of as a radar is, Brad mentioned, it's a non-contact sensor. The radars, as Brad mentioned, has been in play for about the last 15 years or so. Really have got to be very popular. One of the reasons is that it minimizes, eliminates damage and fouling from floating debris and sediment, reduces installation and maintenance cost, and provides good level of accuracy over a wide range of stream stages. And as the image here, this clearly shows a radar installed over a body of water on a bridge structure. And it's just a good explanation of a radar application. We're going to talk more about some of the applications here in upcoming slides. It's a very versatile sensor with various mounting options for many hydro applications, whether it's in a river, estuary, or over a small stream. They're extremely reliable and accurate during major flood events. And just in my view, for medium and large flood events, the radar has been really the most accurate that I've used over the last 30 some years. It's just been a very good and reliable sensor. It does eliminate drawdown from piers and other structures. It's excellent for short or long-term deployment, whether you're just going to monitor a stream for a short period or you're going to use it for a long-term primary sensor. Some of the best practices when you're installing a radar is to ensure the radar is level. Most manufacturers provide a level with the radar. You can also use your carpenter's level as well, but it's important to get the radar level. If not, if it's in on an angle at the time of deployment, if the river goes up or down, it's not going to have accurate readings. The other best practice is you want to make sure there's no obstructions of the radar beam. If there's this minor obstructions like a ladder that's partially blocking the radar beam, there are settings inside the radar where you can have blanking distances. And how blanking distances works is you measure down to the obstruction. You take that measurement and insert it in the radar firmware, and then it's able to block that obstruction out of the way and still read data, still read good river data. Also, you want to make sure you properly ground a gauge. After all, you have a sensor out there in the middle of the bridge, and with proper grounding, you're going to eliminate any kind of electrical issues. So I haven't seen really direct hits to the radar, direct lightning strikes, but what you will have is some residual or static electricity in the area during large thunderstorms that may cause issues with the radar. So again, just make sure your gauge is properly grounded. And the other issue you need to be aware of is a wind effect. So how can you have a wind effect with a radar sensor? Whenever you have a low velocity pool that is subject to major wind events, or even medium or moderate winds, you can have some what we call minor decline in stage. And I'm going to show you a graph that depicts the wind effect. So in this graph here, as you can see at the left portion of the graph, you have a nice rise, it's tracking well. And as you go down the stage and you get to September 27th, you have some dips in data. So that right there is a good signal of that you have some type of wind effect going on. And what the radar senses is it tends to sense the trough of the wave, so you have a minor decrease. So your reading could be reading fine. You have some wind kicking up, causing some waves, and you're going to have a decline in data. When the wind recedes, the radar will come back to a normal stage. So it's just something to be aware of when you're deploying radars. If you have, as you know, low velocity pools may not be the right application for your project. As Gary mentioned earlier in the presentation, is the use of multiple sensors. And so I just want to highlight that in the next couple slides and show you some applications. And so extremely useful during major hydrologic events. You can see these images here. You have catastrophic flooding. And so having that extra sensor or backup sensor is just extremely important to the emergency managers, forecasters, or local entities. And really what it does, it gives them greater confidence in the data to make critical decisions. You know, major flood events can cause damage to infrastructure or sensor. So having that backup sensor is just, it's a good practice to have. So I want to give you an example of a site that's a critical site for forecasting that uses multiple sensors. As you can see in the left image here, we have the orifice line attached to the pier. And then on the bridge wing wall, we have a wire weight and then our radar gauge. As this site, this is medium flow. So right now, the radar data is really good. You have great data with your radar. As you can see with the orifice line, you have slight drawdown. So one would say, why can't I just go with the radar and call it a primary, and utilize the radar just solely? Well, you can see in the image to the right, at low flow, these are braided channels, sand channels, and you may have some sand over that radar, but also this site is really susceptible to wind during high velocity. So it's a critical site for flood forecasting, and so this customer utilizes 2 sensors to get good quality data at all times. And I mentioned drawdown, and I just want to share this with you. This is a radar and bubbler. The radar data is blue, and the bubbler data is orange. As you can see throughout the peaks, the blue is always higher than the orange, and what that is a good example of drawdown data from the bubbler. As you can see in the on the 22nd, on the left-hand side of the graph, you can see the radar is probably close to a foot difference in the bubbler, and then this clearly shows the drawdown of the bubbler. And again, this is a site to where it's critical, and the user wants using a combination to make sure they have quality data at all times. Yeah, I just want to talk to you a little bit about compact radar and telemetry gauges. And these have been very popular over the last 5 years. It really eliminates communication infrastructure to data logger. Instead of running, large communication lines across the bridges, users can simply install a small enclosure with the radar and their telemetry device. As you can see in this image here, it's fully capable of being the gauge the primary gauge. It's this very compact structure to use. It just reduces the installation cost, and it provides a minimal footprint. Over the last probably 3 to 5 years, with the rapid deployed gauges have been really popular, and the RDGs really was primarily in use with large hydrologic floods or hurricanes being forecasted. And they're utilized to augment gauge networks during extreme coastal or riverine flooding, provide situation awareness and support to emergency managers and forecasters, maintain data flow when equipment is damaged, and quick and easy to install. A lot of our users actually have these pre-made in their warehouse, and when there is a large hydrologic event, they will We'll deploy these either at new locations or locations where the gauge has had some significant issues. So it's just a really good system to have. They're fairly inexpensive. You know, when you have a large hydrologic event, to be able to have this system in place and you can easily deploy it, it's just very beneficial. As you can see in the images, they have quick mounts to go on the bridges. Some are measuring met, some are just regular measuring river stage, but it's just a good system to have for a backup.
Thanks, Jim. Good information. So our last one that we want to talk about is the hydroacoustic sensors, and these have come on in the last several years and provide another means, although they're a little bit different technology and as you know, and what they do. These sensors provide the measurement to measure velocity in the body of in the river, and typically there's applications that you would use that, and they of course provide, once they provide the velocity, they can provide the discharge and flow patterns within that column of water. And again, extremely interesting and useful sensors in today's world, and they have their place as well. And the sensor on the right is, of course, similar to a radar, other than the fact that this sensor actually provides a flow measurement, or a velocity measurement, I should say. And so that provides the means for us to be able to provide the discharge measurement and be extremely useful. So again, different technologies. These are a little more expensive than some of the others that we've talked about, and so they have a kind of unique niche of where they are used and how they're used. And we'll turn that over to Jim to explain some of that.
Thanks, Brad. As Brad mentioned, the use of the hydroacoustic sensors, you know, they've become more popular, and really one of the reasons why the hydroacoustic sensors are being utilized is where non-traditional methods are unable to collect data that's useful for discharge. The acoustic Doppler velocity meters, ADVMs, are acoustic current meters that use the Doppler principles to measure water velocities. Water velocity measured by a hydroacoustic current sensor can be used as an estimator or index of the mean velocity in a stream or river to compute discharge. So simply, it's going to give you the mean velocity, and if you know the mean velocity of your channel and your known area or your measured area, you can compute real-time discharge. So it's just a very good, useful new technology that's being implemented. As you can see in the upper image, you have a submerged sensor. That is really how it works. It's, as Brad mentioned, it's going to go take samples throughout the channel, and they're collected in cells, and the sensor analyzes these velocities and is able to compute a mean velocity. So that's a good example of the submerged sensor. And then there's new technologies out that are non-contact that will measure the velocity of the surface. And really, one of the general applications and why the acoustic meters are being used today, they're deployed where variable backwater or unsteady flow conditions exist, in stream confluences, streams running into lakes, or tidal effects. So, you know, whenever you have variable backwater, you know, non-traditional or traditional methods will not work, or are very inaccurate. So this is one of the main reasons why these sensors are more and more popular. One thing to know, you can get continuous discharge of rivers, open channels, and canal with known and stable channel areas. So they're best utilized when you have a site with little change in area. And what that means is that your bed isn't changing, your area is not changing. So a good example is in the lower image where you have a velocity meter in a canal where you're not going to have that area change. So those are really the best recommended use for those sensors. Other deployment applications measure profile of a water column to determine current patterns in bays, harbors, estuaries, lakes, and rivers. Many researchers utilize these sensors for their research projects and also to operations and shipping and other applications. Certain velocity sensors deployed by submerged, as I mentioned, in channel, and other sensors are non-contact, which are mounted on structures. One of the things that you have to realize, they're not sensors you can simply just deploy. They take maintenance. So at least once a year, depending on the site, you need to inspect the sensor, clean any kind of algae or any other type of debris off the sensor. So one thing they do require some maintenance, and also it takes a tremendous amount of data collection to develop a rating curve. One of the best practices, once you have a sensor location, you want to keep that location. Once you establish a rating, if you move that sensor, your rating that you just took, maybe months to develop, or you'd have to redevelop that rating. So it's just something to keep in mind. They do take a fair amount of maintenance, and also the data that you receive from these sensors, you have to process that information to get your best possible data. So we covered a lot of ground today. As Brad mentioned, the technology side, I tried to give you some best practices, and we just thought we'd want to put together a table here for you for future reference for some of the different situations or characteristics of your deployments to just use as a reference. The ephemeral stream and intermittent streams, a PT or radar if you have structure, or you possibly can create structure there as well. The second choice would be the bubbler. For a watershed with shallow depths, rapid stage change, the pressure transducer. Also, the radar would be your second choice. So open channel with stable control, we recommend the radar and the bubbler. And also a control pool is affected by wind. You may want to use combination, but the bubbler may be your best choice, and a pressure transducer. Large rivers with high velocities and debris flow, radar would be your best alternative with the bubbler as your second. As a reservoir, as Brad mentioned, if you have a stilling well there, they're great. You can utilize the shaft encoder, the bubbler, and also if you want to back up, you can utilize a pressure transducer. For the variable backwater situations, really the only sensor there is the hydroacoustic. So hopefully this gives you a good guide for future reference. Again, what Gary mentioned, each site's different. You have to make that decision given your infrastructure you have available. Sometimes it's a room in your gauge house, but hopefully this has been helpful for you, and you can utilize it in the future. I do want to talk a little bit about just what AEM is doing, new technology and products that we're working on. We talked about the sensors that are available now, but at AEM, we're looking towards the future and looking to invest new technologies and new products for our customers. And one of those new products is a hydro camera utilizing artificial intelligence. And how this would operate is your camera would be pointed towards a staff, And the camera is going to be a smart camera, and it's going to be able to determine what the river stage is by just viewing the staff gauge. So that's really exciting for the future. Other product is a non-contact ultrasound and radar technologies to measure water level, surface velocity, and discharge. And as we mentioned about sensors and the different applications, you still have to get that data back to your database. And so we're constantly working to enhance software to manage the hydro network. We just feel like making that investment so our customers can easily manage their system, have tools to better manage their network, is something that AEM is dedicated towards. And I appreciate your time today.
Thanks, Brad, and thanks, Jim. You guys did a fantastic job. That was really informative. I just want to comment before we get to, we only have one question here, but you may wonder what AEM is. It's Advanced Environmental Monitoring. FTS, High Sierra Electronics, and One Rain are all part of AEM. And so when Jim's talking about what AEM is doing, he's commenting on what a number of the brands from AEM may be working on. And so there's a number of solutions that we could provide. So if there's any questions based on things that you heard today or information, we have people that can help not only answer questions about the things that were presented today, but about other solutions and future developments and so forth. Just by way of information as well, some of the other brands that are in part of the family of AEM, Davis Instruments, Earth Networks, Lambert, the View. So you may be familiar with some of those brands, and so we can certainly create solutions based on all of those. We only have, that I can see right here, one question that's pretty easy. Will you send out a link of the recording of this webinar? And the answer to that is yes. It should be on all three of the websites within a day or two. If anyone would like it sent to them directly, just let one of us know, and we could certainly get it out to you. This is our contact information, Brad, Jim, and myself. If you'd like to get with one of us or, again, anyone else in the company, please let us know, and we'd be happy to chat with you about different types of solutions for your guys' networks and your needs. So thanks again for joining us. Been fantastic. We're glad you took time out of your day.